this lesson, we're going to examine trigonometry as it is placed on the Cartesian plane. We're going to call this rotational trigonometry as opposed to straight line trigonometry because we're going to be moving around in a circle. So, a starting point for us. We want to determine the angle that's made between the x-axis and the line that starts at the origin and passes through the point 3, 4. So if we were to draw that, obviously the origin's here. The point 3, 4 would be up here somewhere. And if I drew a line that goes through there, we can see that we have an angle formed right here. That's what we're being asked to find. So let's figure out that angle. How could I do that? Well, really, if you think about this, there's actually a triangle here, right? This is 3 on the x-axis, and we've gone up 4 on the y-axis. So couldn't we use tan to solve this? The tan of theta equals 3 over 4. Oh, sorry, not 3 over 4, 4 over 3. Opposite over adjacent. If I want to solve that, I can use an inverse. And if I put that into my calculator, we should end up with, a second here, 53.1 degrees. All right, so I've got that angle. It also asks what other ratios can be used to find this angle. Well, how else could I have found that? I can use the other ratios, sine and cos, if I were to know the hypotenuse. Can I find the hypotenuse? Sure I can. A squared plus b squared equals c squared, because this is a right triangle. So if we do that, we get 25 for h squared, or in other words, h is 5. So now I could have used the sine of my angle, my opposite, over my hypotenuse, and used inverse sine. And if I do that, I hopefully get 53.1, because that's what we know the answer is. Or I could use the cos of my angle. Again, different ratio, same idea, inverse, and again I should get 53.1. So if I know 2 of my 3 sides and the angle between them, I can use any of my ratios, right? Because I can always find the third one by using Pythagoras. So our objective today is to attack questions that look like this. Things that are being placed on the x and y axis, where we can get points, which are really the sides of our triangles, and use them to find angles. So here are some ideas. When we place the line on the coordinate axis, it always rotates around the origin. We call this rotational trigonometry. We're always going to begin at the x-axis. That's our 0 point. So 0 is always here, our initial value. And we're going to end wherever we decide to stop at some point. We call that the terminal arm. So notice that this is counterclockwise this time, as opposed to bearings, which were clockwise. That can cause a little bit of confusion. Since if we were to keep rotating, we would make a circle. We can talk about the equation of a circle being x squared plus y squared equals r squared with a center of 0, 0. That's a handy idea because it kind of looks like Pythagoras. A squared plus b squared equals c squared. Except instead of having c, we have r as the radius of a circle. Okay, so what we're going to do is take the ideas of SOHCAHTOA and apply it to the circle. So in SOHCAHTOA, we have an angle in the bottom left corner here, opposite adjacent hypotenuse. If we draw that onto our circle, we end up with still the same angle, bottom left corner, but now we have ourselves a triangle at some point x and y, and we know that this distance from the center out to that point is called our radius. So I'm going to start using the letters x, y, and r. R is the radius of a circle, x is how far we've gone along the x-axis, y is how high above we go the y-axis, and then we could take our SOHCAHTOA letters and put them into letters that will help us do rotational trigonometry. We're going to call this Sir-Six-er-Tix. That sounds real confusing, I know. But if we take the same letters, x, y, and r, if we think about our angle, I hope you would agree that my opposite in that triangle would be y over r. So S, Y, R, Sir. When I do cos, that would be my x over my r. EXR, sixer. And then when I do my tan, I get y over x, and that's my ticks. Sixer ticks. It's a new word for us to remember. Unfortunately, we also have some new ratios. So we only ever talked about the primary ratios, sine, cos, and tan. We're going to have new ones for this unit. We call them cosecant, secant, and cotangent. And the way they work are they are the reciprocals, the upside down of the corresponding primary ratios. So the one I like to remember, well, first of all, tan and cotan are pretty easy to remember. But the other ones are S becomes C and C becomes S. So sine is cosecant, cosecant, sine, and cos is secant. Yeah, it's a lot of stuff. I would say learning goals are really important for this unit. Lots of stuff to put on there. So sixer ticks, sine, cos, tan, and then cosecant, secant, cotangent. What are we going to do with this? Well, just the basics today. So the coordinates of point on the terminal arm in standard position are shown. In other words, they're telling us we started at 0, and we rotated counterclockwise around until we got to here. And then we've got a point, an x and a y. We want to figure out the exact values of the ratios. I don't care what the angle is today, just the ratios. So to do that, I know x is negative 24. I know y is 7. I need to find r, the radius of this circle. I can do that by using Pythagoras. A squared plus b squared equals c squared, or x squared plus y squared equals r squared. Now I put them out of order. I put 7 first and negative 24, but it doesn't make a difference. The idea of Pythagoras is a and b are interchangeable. If we do this, we get 625 equals r squared. So r is 25. Now one thing people might be asking about is, well, if x and y can be positive negatives, can r? The answer is no. R stands for the radius of a circle. R must be positive. There's no choice on that, okay? So, primary ratios. Sixer, ticks. So my sine ratio is going to be the y value, which is 7, over the r value we just calculated, 25. I'm also going to do I'm going to cheat here. I'm going to do part A and B at the same time. The reciprocal ratios. The reciprocal to sine is cosecant. S goes with C, C goes with S. And what I do is I flip my fraction. Cos is x over r, so negative 24 over 25, and yes, it's possible to get negatives now. Cos goes with secant, r over x, so 25 over negative 24. Now negatives can go top, bottom, or in front, but the fact is you need to have one negative in that ratio. And then tan theta equals ticks, y over x, so 7 over 24. And as I said, negatives can go anywhere you want, so I'll put the negative in front. And then cotangent, opposite upside down, so 24 over 7. It needs a negative sign there somewhere, so I put negative in front. There's my 3 primary and 3 reciprocal ratios for that piece of information. Part C, use one of the ratios from A to determine the value of theta. So I have a choice. I have any one of these 3 equations I can use to find my angle. How do I find the angle? I take an inverse. So I need to take the inverse of one of my ratios. Which one do I want to use? Well, I like using positives. I think positives make my life a little bit easier, so I can use the first one. So theta will be the inverse of 7 over 24. Now you can use any of the other 2. You can use cos, you can use tan. It doesn't make a difference. As long as you're using an inverse, you should get 16.3 degrees. Now wait a second. Look at our picture. That answer is not 16.3. What have we just found? Well, when we use rotational trigonometry, here's a little trick for us. We're always finding the angle inside the triangle. So I've calculated 16.3 being right here, the angle inside the triangle that I used. But theta, the question actually in the rotational stuff, is this angle on the outside. So how do we get that? Well, call theta 1 and theta 2. This is the one we actually want. We know straight lines make 180. So if I know the inside angle is 16.3, I can subtract it, and I should be able to get the outside angle. My answer should be 163.7. Okay, so lots and lots of information there, right? We have to be able to use Pythagoras, or the idea of a circle, to figure out r. We can set up ratios, 6 of them, using 6 ticks and the reciprocals. And then we can actually solve for angles. But remember, it's always the angle inside a triangle. That's how trigonometry works. We're making triangles here. So I have to interpret my diagram. Do I have the angle I want, or do I need to do a little bit of subtraction? Okay, we're going to try something different. Find the exact value of the other 5 trig ratios if it's known that cotangent of A is negative root 7. So I need to interpret. Oh, there's also some other information. And A is between 270 and 360. What's that telling me? Well, 0's here. Remember, we're going counterclockwise now. Angle A is between 270 and 360. In other words, it's trying to tell us that our line's got to go down here somewhere. Okay. What else are they trying to tell us? They're trying to tell us that cotangent. How does cotangent work? Well, if I go back to Sir Sixer 6, cotangent of A is negative root 7. Now, tricky here. That's actually over 1. And cotangent is the opposite of tangent. So tangent is actually 1 over root 7. There's a negative sign in here somewhere. And then I think about ticks. So my y value and my x value. Now, we said the negative sign's in there somewhere. So either the 1 is negative or the root 7 is negative. So if I look at my diagram, which is negative, the y direction or the x direction? And looking at it, I'm going down. That's negatives in the y's, right? So the negative is actually attached to the 1. The x, which is going to the right, notice that's the positive direction, is root 7. So by giving us this information about where the picture is and what one of the ratio is, I can actually figure out all the other ones. I've already figured out one of them, the tan ratio. Now I need sine, cos, secant, and cosecant. But for all 4 of those, I need to know the r, the radius of this circle. So I need to do x squared, or a squared, which is root 7 squared, plus b squared equals c squared. Root 7 squared, that's just 7. Negative 1 squared is 1. So I get 8 for r squared. So r is the square root of 8. Now, tricky thing here for us. We talked about exact values in the past. When we square root things, if we can't get a nice number, we have to simplify the root. So back in our memory banks, we learned how to simplify root 8 into a perfect piece and a non-perfect piece. So for r, we're going to be using 2 root 2. Okay, we want to simplify our radicals. Okay, let's find our expressions. We already found tan. Let's find sine. Sine, Sir Sixer 6. Sine is y over r. My y value is negative 1. My r value is 2 root 2. Oh, but there's a problem. We're not allowed to have roots on the bottom of radicals or fractions. How do we get rid of that? You might remember the idea of rationalizing. Multiply the radical by what you want to get rid of. I want to get rid of root 2, so I multiply by root 2, top and bottom. What's that going to give me? Oops. On top, negative 1 times root 2 is just negative root 2. On the bottom, I can get 2 root 4, or in other words, 2 times 2, or in other words, negative root 2 over 4. Okay, so that's something else we're going to learn about, rationalizing things. Here's my sine. We said it's nice to write down the reciprocals at the same time, so let's do that. The reciprocal of sine is cosecant. I flip it over, I get 2 root 2 over negative 1. It's okay to have radicals on the top, totally fine, just not on the bottom. And it would be okay if you'd have your answer like that, or if you want to simplify it, that would be the same thing, right? Divide by negative 1. Okay, we've done 2 of them. We need 2 more. We got to find cos. So the cos of theta equals x over r. X was root 7 over 2 root 2. Uh-oh, radical on the bottom again. That's rationalized. Root 2, root 2. That's going to give us root 14 over 2 times 2. We just did that a second ago, right? Which is root 14 over 4. And if root 14 broke down, we would try. But unfortunately, there's no perfect roots that go into it. And there's cos. We need secant. Secant is the upside down of cos, the reciprocal of it. So if we just go back up just a little bit, we end up with 2 root 2 over roots. Oh no, another radical on the bottom. We got to rationalize. What radical do I want to get rid of this time? The root 7. So root 7 gives me 2 root 14 over 7. Okay, notice we didn't just flip the final answer from the previous one, right? We went back to the beginning and flipped it because we need to rationalize every time. Yeah, that's a tricky one. There was lots of parts and pieces there. Okay, lots of things to think about. Okay, last idea. How do we actually use this? The best use of this is to find exact values of angles. We don't have a calculator anymore. We can find what is the answer without using a calculator. We can do it in an exact way. So let's look at this example here. Sine 30, cos 30, tan 30. If I draw that from 0, 30 degrees would be here. If I were to actually punch that into my calculator, sine of 30, so take your calculator out, we get 0.5, which I hope you agree with 1/2. Well, based on Sir Sixertex, I now know that the y value is 1 and the r value is 2. If I were to make this into a triangle, y is 1, r is 2, I can find x by using Pythagoras. I'll get x squared equals 2 squared minus 1 squared. Make sure we do exponents first. And now, if I really wanted to, I could find the exact value of cos. Cos of 30, without using a calculator, x root 3 over r, 2. I could find tan of 30, x, y, 1 over x, root 3. Or if I rationalize that, I get root 3 over 3. And if you were to try it with your calculator, I hope you would agree that those are the exact same answers that we get. And so what we're going to aim for tomorrow is we're going to start evaluating angles without calculators anymore by making little diagrams about the sides of a triangle and using Sir Sixertex to figure out the ratios that go with them. And that's our objective for rotational trigonometry. Today, we're going to start with a little handout. We're just going to do the first 2 questions, just setting things up. I don't really care what the angles are today. That's where we're going to go tomorrow, but I need to be able to set them up first before I can get to that point.